All right, yeah, sorry about that. Trying lower settings. So I'll continue on here. I'm back to streaming for them. We'll see if anybody else can join. So, all right. Hopefully I didn't lose the. So I think I correctly created a second stream that time. We'll see if I got. We'll have both parts of this here. So as I was saying, I was going to just maybe kind of remind about the workflow for the assignments. Let's go ahead and create commit, make certain my notebook is still running all the cells correctly. So do use good commit messages. So we'll test that the notebook runs all cells cleanly. Yeah, we're still having some performance problems, I think. Go ahead and push that up. So the thing to check, I haven't had a chance to check everybody, but the thing, do kind of be aware of your stuff in the pull request, and that you are getting things showing up here as you're doing your work. So. So this is the one that I just did at this moment. It's actually still running here. So yeah, if you do it fast enough, you'll be able to watch the GitHub workflow running on the stuff. So in this case, if you've been looking at this stuff, the dependencies can be kind of long. You probably don't have to look at all those. But then but yeah, the most important stuff is the run here, and checking that the stuff is running here. So for the notebooks, your notebooks always should be running, right? So you do want to check that this check for the assignment notebook runs all cells cleanly is getting a green check mark in there, right? So again, yeah, some people had some problems with their kernel, so it might be that you're actually okay, just need to get the kernel set correctly. But then, right, check these other things. So as you're doing the tasks, you do want to check that when you push it up here, that those are doing the same passing or not as you work on them in your own assignment notebook, and the source code files as you're completing each one of these functions you're supposed to write. Okay. Continue being a little bit slow here, so don't know if we're going to be able to keep going. All right. I think those were kind of the main stuff. Did anybody have any other thing they wanted to ask about? It's kind of like the last chance. I will have the normal office hours. Of course, you can email me. I am looking for this stuff by Friday. Although, you can probably keep working on it past 5, but I might be doing some evaluations of this over the weekend, so you should try to get it in by Friday. And I don't think I've had anybody asking about needing more time, but yeah, my plan right now is to look at the stuff probably starting Saturday sometime, maybe. So, I had a question about adding in the import statements. You do have to add in import statements. You might have to add them in the assignment notebook that's given to you. One thing on that, if you read the comments on these, is it's another kind of standard or best practice thing when using notebooks. Usually, usually all of the things that you use in the notebook should be imported at the very top. So they shouldn't be scattered in there. Now, I violate that. So if you look at my lecture notebooks, I violate that a lot. But there's a reason for that, because I'm usually discussing a particular library or a particular machine learning algorithm from a library. So, we discuss or show how you import it interleaved as we're talking about stuff. But for most notebooks, that's not really the point. So you really should have everything at the top. And I gave some stuff to begin with, but everything, you might not have everything you need. So yeah, I think you do have to import some stuff. So it is fine. It is kind of conventional in notebooks for like sklearn to import individual things one by one. So there's a couple of examples of that. So you could do that to get like the pipeline if you needed it, or some things like that. But also, though, you will have to have an import, add some imports into the assignment tasks as well. So again, though, those should be at the top, so those shouldn't be scattered around. But you definitely will need to add in additional imports. You will need them both in your assignment tasks source file and in the notebook. So. Okay, but yeah, good question. I don't know if anybody had any questions about StatsModel or not, but there is an example lecture video and an example lecture notebook in the class resources. Again, I'm not expecting you to kind of really understand StatsModel logistic regression. I just wanted people to get an example of using it. So, I mentioned this last time. I might not have made it to my live stream, but just be aware that StatsModel has some slight differences on the API from the from scikit-learn. So the biggest one being that you pass in the labels and the data that you want to fit in the reverse order that scikit-learn does it. And the other big one, though, is you do need to by hand add in, call a function to add in what's known as like a dummy intercept parameter for x. And if you don't do that, you won't quite get the right. You probably won't be able to pass the tests for this last one. Because you won't get the right fit for the logistic regression model using StatsModel. So you kind of maybe don't know why we're doing that or understand that, but starting next week when we get into the details of logistic and linear regression, hopefully that should make a lot more sense what that is, what the intercept parameter is on your input features and why it's not. So basically scikit-learn by default is just adding that. It expects it not to be there and it adds it for you. But StatsModel, because of the way that statisticians perform linear and logistic regressions, they don't expect it to be in there normally, and they put it in themselves by hand if they need it. Okay. So, so I thought I would go back and talk a little bit about some of the stuff for classification. So we were looking at the classification notebook last time. So unless anybody wants to bring up something at the last minute here on the assignment 2, let's move back over to looking at some of the resources from for this unit for this week here. So let me go ahead and close this off and open back up my class resources. So yeah, whenever I'm switching between containers, I usually do that, do the file close remote connection, and then once you have a container created, it's usually easiest just to go to the remote explorer and restart a created container that way. So, and slow it down a little bit again here. So. All right, so let's go back to the class resources here. Hopefully this will come up. So one of the things that was asked to be done on the assignment 2 was to show like a confusion matrix. So I was going to jump back to that and maybe talk just a little bit, 10 more minutes about the how you evaluate a classification problem and doing the precision and recall maybe. So I always have to kind of remember, I always get confused trying to remember, okay, what exactly is precision and recall doing, and also in future, the next assignment 3, I'm ask you to do some more of that, and also including create like an ROC curve. So I wanted to maybe mention those real quickly here this week when you were supposed to be looking at that stuff. So. Yeah, things are still being slow. So I had somebody ask about that. I mean, if you get that, most likely, you just didn't find the actual most recent run. So the no-hup file, it actually appends on the end there. So you do have to maybe search, make certain you're at the last one, which would be the one that's actually running right now. So that's usually the reason why it says you need to give a token or something when you click on that. You're just not using the one that's actually running in Jupyter, in your Jupyter lab. So. Oh, there it is. Okay. So. I might avoid trying to rerun this here because I'm still not running very smoothly, I don't think. So kind of one of the last things that we were talking about before I switched over to assignment 2 on Tuesday was these things here. I wanted to mention a thing again. I mean, it is good for you taking this class to make an effort to understand precision and recall, the stuff that's done here. So this is a fundamental thing, this is the basic thing that people, when they're doing a classification, the first thing they'll do is ask, okay, what are your precision and recall scores, and show me a confusion matrix to get an idea of how well your model is doing at classifying some data, right? So if you you can do the same stuff if you have more than if it's so we're looking at binary classification here. We've only got 2 classes, true and false. I mean, the same concepts can work for a multi-class classification, but we'll stick with binary classification for right now, right? So the confusion matrix is easy to get, so you can use one of the methods. So we showed an example of generating a confusion matrix like this. So there's some examples. You can make a nicer plot, so you can plot this to get some encoding by color to visualize it better. So it's not really necessary when you're doing binary classification usually, but if you have a large confusion matrix, because you like if you're doing a confusion matrix for MNIST where you have 10 classes, it can be helpful to actually visualize it, to use some color to show which are high and which are low values in your confusion matrix. So, but yeah, for our basic binary classification, we get something like this. If it's laid out correctly, it should be in this order. So that's the output that you'll get from using the functions in scikit-learn to compute a confusion matrix. So you get the actuals are your rows, and the columns are your predicted. So from that, your diagonal, and it goes 0, 1, 2, 3 from top to bottom on your rows, and 0, 1, 2, 3 from left, or 0 is false or negative, and 1 is true or positive for the binary classification. So that means that your diagonal will be your true, the things you got correct, your true negatives and your true positives. Right? So I mentioned last time the false negatives are the things where so in this case we're making a 5 predictor, so those were where it was actually a 5 and we predicted it wasn't. So we falsely predicted negative, falsely predicted 0 in this case. And vice versa on this one, so these are the things where it was actually not a 5, but we falsely predicted it was. False positives. Okay? So I can never really remember precision and recall, but it was good. So precision, this is a good kind of summary of it. Both of these are using the ratio of the true positives. So precision, then we're doing it the ratio. We're looking at false positives basically, and recall we're looking at false negatives, concentrating on those and the two things. Okay, so that's the only difference between these two here. So these can be important in the real world. So precision is going to be, so in this case, we're 3 out of 4. So if you do that calculation for precision, we're saying that we have a 75% precision score because we had one incorrect, one false positive out of the things in this column here, right? So among the stuff where we predicted positive, one time we were wrong on that of the 4, right? For the 3 out of 4, right? So when I look at these, when I do this, this score is telling you, basically how often you're doing false positives. But the reason why that's important is, so think about this like let's say you're making a classifier to try and predict whether somebody has cancer or not, okay? So usually I find that helps clarify if you think of something more specific. So in that case, false positives for a cancer predictor are the cases where the person didn't have cancer, but you falsely detected that they did. Okay, so think about what happens for that, and that's where precision is measuring. So in that case, you're saying they have cancer when they don't. So the costs of that are you have to go maybe do some more testing. You're going to worry the person, right? So there's additional costs, some additional mental anguish until they maybe hopefully go and clarify that out with a more detailed test to find out that it wasn't true on this test here, right? So that's bad, but for like cancer prediction, the false negatives are even worse, because false negatives are the case, and this is what recall is measuring here. These are the cases where the person actually had cancer, but you falsely are telling them that the test is falsely saying that didn't detect it. Okay, So for like a cancer detector, the consequences of that are somebody could die. So they go off and they think they're fine, and the cancer progresses to some point where they can't actually do something about it. All right. So, which one is more important, recall or precision? False negatives or false positives depends on your application. So, where it's life or death, usually you want to minimize those recall errors. Right? So for a cancer detector, you'd like to get those recalls to be 100%, where you're having no false positives. You're getting 5 out of 5 and 0 out of 5 on the 5 out of 5 true positives and no false negatives on your recall there. All right? But it depends on the application. So that's it. For some applications, it would be more important to emphasize precision. Okay, so you can handle a couple of false negatives, but it's too expensive to incorrectly say that somebody that this was true when that wasn't. Incorrectly indicate that. That it was in the true class when it wasn't. Okay? So, anyway, so there's always for a given model, there's always a trade-off between precision and recall. And in fact, that's what these curves are about. So the way that a classifier works is when you stick a number in and ask for it to predict, it's going to actually give you a value that's in some range. So for binary classification, we have to just pick a threshold and say if the result was less than that threshold, we're going to predict negative or 0. And if it was greater than that threshold, we're going to predict positive or 1. Right? But you can change that threshold, and that's what's happening here when you plot precision recall on these curves. So typically the default is 0, right? So for 0, you would get this measure for recall, so 0.65 or something, and this measure for precision. But if I were to make it a little bit smaller, like negative 2,000, I can emphasize, I can get perfect recall or almost perfect recall, but have bad precision, right? So I'll be making a lot of those type 1 errors, given a lot of false positives, right? But yeah, for the cancer example I was talking about, that might be what you want to do, right? So because you want to eliminate, you want recall to be as high as possible. You want to eliminate false negatives. People that have cancer that you're telling them that they're fine at the moment from the test. Right? So you could do that by going this way on this threshold. Have recalls close to 1 or high to 1 here at the cost of having some false positives. Some false positives. Yeah. So that's what. So like the assignment 3, I think asked you to do these and also do like an ROC curve. So for a given model, you can tweak the trade-off between precision and recall. But the real thing you want to do, if you can't find a good compromise on that, you can always try and build a better model. So you can end up with a model that, if you look at these curves, where recall is 1 for a lot larger of the range, and precision is 1 for a lot larger of the range. So in that case, if you're plotting precision and recall in the same graph, a better model would be one where both of these over the whole range are 1 or close to 1. Right? Sometimes you can get so instead of using a basic logistic regression, maybe I use a support vector machine, and it'll perform much better. You won't have to make so much of a trade-off because there'll be ranges where both precision and recall are really high in a better model. Right? So that's when you're talking about building a classifier, that is something to think about. So for a given model that you have, you can tweak the precision and recall if you need to, but if the performance that you have is not good enough, you might have to go and try and build a better model, one that does better over the whole range for the precision and recall. Okay? So instead of plotting these separately, you can plot these on one, so you're getting a similar idea, and this leads up to the idea of the ROC curve, but here all we're doing is, instead of having that threshold, we just plot precision versus recall as we're going over that range, right? So if you plot these versus each other, often a good choice is somewhere around the elbow, where you're given a good balance of precision and recall for these things here. This is directly from the textbook chapter. So this was showing this threshold here, I believe, where we had like a 0.5 on the recall, but a high precision. So here we're getting high precision at the cost of recall is around 0.5 or a little bit below 0.5 here. So if I want high recall, I have to go over here, but precision is going to start going down. Okay. So I just mentioned, so this is a common thing if you see people reporting classification, they might just jump right to doing ROC, receiver operating characteristics. It's a similar idea to this. So if you understand this, we're just not plotting. In some ways, I actually find this better to use because this you can directly read out, recall and precision, the trade-off for them. But I don't know. This is just standard, so you'll probably see this a lot. So it's really using the recall is actually the y-axis, but instead of precision, they're using this fallout on the other one. But yeah, it's plotted one against the other as the threshold changes. So for both of these, basically, a better model is one that has more area under the curve, right? So this might be a logistic regression model. If I built a support vector machine model, it might have more area under the curve. So it might be look up there, right? So if you're comparing separate classifiers using that or using ROC, if you put them on the same plot, you can directly see which one does better because the one will be have less area and one will have more area under the curve. So the one with the more area is a better model for the classification task that you're trained it with. All right. There was an example of this. So here we were using a basic stochastic gradient descent. The textbook was using that, but we can get a much better performance, and we can tell it's much better performance using the precision recall or the ROC curve by comparing the area when you trade off those things. So you get much more area under these curves for the random forest. Right? Random forest is one of the models we'll look at. Random forests are one of the better basic machine learning algorithms that we're going to look at in this class. So forests and different kinds of ensembles. A lot of people use those for lots of problems. So here's the same thing for using the ROC curve. Get the same conclusion if you plot it as an ROC curve. So. All right, so I think I did want to mention that again. We didn't quite get over to those details, but that's one important thing to know about classification. So how you measure the performance of a model that's doing classification and how you can compare different models. So those kinds of things, recall precision, and then plotting those together and looking at the area under the curve. Those are the standard basic ways if you look at people reporting results on classification problems that you'll see them using. All right, so yeah, that's it for today. Any last questions from people that are back with me on live, or are you guys that are here? So we got a few more minutes, but I'll go ahead and end it there. Let you guys go. So keep working on the assignment 2. Send me emails or stop by the office hours today if you have a question or something. So. But yep, that's it. That's it for today. I'll see you guys next week. And we'll start on logistic regression next week. So yeah, see you guys.